Hey everybody, so here are the solutions for the practice test for energy, motion, and simple machines. And I'm still kind of working on the format of what that's exactly going to look like, but um, we'll get that taken care of sometime soon. So first question here was an 80-gram ball thrown upwards at 9.6 meters per second from 1.8 meters above the ground. Use energy equations to determine its speed at ground level. So basically something that looks like this. We have point 1, 0.2. Ball is going up at 9.6 meters per second here. And how fast is it going when it actually comes back down and hits the ground if it starts 1.8 meters above the ground? Um, Again, we have our three types of energy that we've been using for these types of problems. We have gravitational potential energy, elastic, and kinetic. Gravitational potential energy is based on height. So at that first position, we do have gravitational potential energy. We are off the ground. We're also moving, so we have kinetic energy. That is mv1 squared over 2. And we don't have any spring or anything being stretched or compressed, so that's not part of it. No elastic. When we get to 2, we no longer have a height, and we are only moving. So all our energy at the beginning has been converted from gravitational and kinetic to just kinetic. So then it just becomes a simple matter of plug and chug everything in. We don't care about the mass of the ball, that doesn't matter. So we'd have 10 times 1.8 meters plus 9.6 meters per second squared over 2 equals v2 squared over 2. Moving everything around and solving for that, you end up with v2 being 11 meters per second. Again, key there is we're just converting energy types, right? We're starting with a height and motion, which is these two here, and we're moving to just motion at the end at point 2. Looking here at the second problem. So now we have a bow. We're going to pull that bow back 61 centimeters with an average force of 140 newtons, kind of pulling it back in this direction. Okay. How much potential energy stored in the bow? Well, in this case, we do have our potential. Sorry about that. Our potential energy is our elastic potential energy, which is based on the amount of work done. So that's the force times the distance. And now work we put into the bow becomes potential energy stored in the bow. So we have 140 newtons, but we have that times the distance of 0.61 meters, making sure we do our unit conversions correctly. If you don't do that, you'll end up with a different number. That is not correct. Distances need to be in meters. So we have 85 joules worth of stored potential energy in our bow. Now in part B, it asks for, we have a mass arrow with a mass of 86 grams shot from the bow, pulled back the same distance. How fast would it be going? Well, that's where we would be converting our elastic potential energy into kinetic energy. As we're going from that stored energy in the bow to what is now the speed of the arrow as it leaves. So we know that 85 joules is going to equal 0.086 kilograms. Again, masses need to be in kilograms, times v squared over 2. It's the only thing to be careful with there. For the most part, problem's pretty easy, but make sure you get that mass conversion correct. And then if we solve for v2 based off, or the velocity based off that, we end up with the speed of the arrow of 44 meters per second. We solve that the right way. So first two problems are all about just converting energy from one form to another, understanding our three basic types of energy we were dealing with. Next one's another similar thing. We have a table, we have a spring, we have a lab cart on top there. Okay. The physics lab cart was compressed 12 centimeters with 44 newtons of force. Okay, we want to know, first part is how much potential energy is stored in there. So again, this is elastic potential energy. So we're F times D. We have 44 newtons, capital N for newtons. we have a distance of 12 centimeters, but again, that needs to be in meters for the units to work out correctly. So 44 newtons times 0.12 meters means we put 5.3 joules worth of energy into our system by loading up that spring. Now it turns out the lab cart has a mass of 750 grams. We want to know what's the maximum speed that the cart's going to attain. So again, that's going to be converting our stored elastic potential energy into kinetic, just like the bow and arrow problem in the previous one. So 5.3 joules of stored elastic energy is now going to be kinetic, and the mass of that is 0.750 kilograms over 2 times v squared. When we solve for that, we get that v is 3.8 meters per second. So the maximum speed that cart's going to attain after the spring is totally done giving all its energy to the cart is 3.8 meters per second. Again, where we've converted all of our stored elastic energy into kinetic. In C, now that cart's going to go flying off the lab table. Okay, we're going to assume that's at that speed that we found. We want to find out how far horizontally it's going to go if the table is 92 centimeters high. So this is kind of like your rehash of first semester projectile problems. So again, we're trying to find a distance in the x-axis, how far it's going, dx, and that is always vx times t air. No matter what, remember the speed horizontally isn't going to change in our problems because we don't have air resistance. We know that vx is the 3.8 meters per second. Assume the table is perfectly flat. Didn't tell us any different, so we're going to assume that it's perfectly flat. And we're launched off perfectly horizontally. So question becomes, how long does it take to fall? Well, time in the air is the square root of 2 dy over g. So we have the square root of 2 times 0.92 meters. Again, this is my dy here. This is how far we're going to fall. But we need to make sure those units are in meters. Again, to make sure everything matches up, over 10 meters per second squared. So that time to fall is 0.43 seconds. So 3.8 meters per second times 0.43 seconds means it's going to travel 1.6 meters away from the table. Again, probably not going to have any projectile to do with this, but we will be doing that on the spring exam when we get to that point. So make sure you still kind of sort of remember how to do that and be ready for that. Next question. Ramp is used to roll a piano onto a stage. So here's our ramp, and there's our stage height right there. The ramp is 8 meters long, and the ramp is 1 meter high. Piano has a mass of 240 kilograms. I know the IMA of the ramp. Again, this is the ideal mechanical advantage. How much of benefit should I get from using this machine? That has nothing to do with the forces applied. It's purely a ratio of distances. So that's going to be d in over d out. Since we are going to go 8 meters to only go 1 meter up in the air, again, in is the side we work. This is the in right here on the ramp, and the 1 meter is the height of the ramp. This is the output side. Is what we put in is walking up the ramp. What we get out is we go from the ground to that height there. So we have 8 meters over 1 meter. It means we should get a benefit of 8 by using this machine if no energy is lost. Second B asks for weight of the piano. Again, weight equals m times g. So 10 times 240 kilograms means the piano's weight is 2,400 newtons. Ideal force is necessary to push up the ramp. Well, that's F in. Ideally, remember, F in. Ideally, the work we put in should be equal to the work that we get out. And we just need to define everything correctly. So if we do that, the distance in is 8 meters. F ins are unknown. F out is the weight of the object, because that's what would have had to do without the ramp, is the 2400 newtons times the distance out, which is 1 meter. So if we have 2400 times 1 divided by 8, well, that tells me that the ideal input force is only 300 newtons. Again, because we're getting that benefit of 8 for the machine, ideally, 8 times the force we put in should be equal to the output force. But in reality, we tested it and we found out that the actual Fin, the real Fin, is 400 newtons. So what does that mean? Well, obviously our ramp isn't perfectly efficient. When we didn't hit the 300 newtons, we had to put in more force than that. So we want to find out the actual mechanical advantage. And AMA is always what we got out divided by what we actually put in. So in this case, we got out 2400 newtons, but we put in 400 newtons, which means in reality we got a benefit of 6. We're hoping for a benefit of 8, we only got a benefit of 6. So for E in efficiency, that's purely our grade, which is going to be the AMA over the IMA. So we got a benefit of 6, we were hoping for a benefit of 8. That means that we were 75% efficient in terms of using this machine. So again, ideally, no forces, no energy is lost, okay? But in this case, energy was definitely lost. It took us an extra 100 newtons to push the thing up the ramp, which means there's probably about 100 newtons worth of friction working against us. Okay, this one, compare the kinetic energy of a car going V when it's going to V. So we have two situations here. We have KE1 and we have KE2. We know that both of these are, that's how we're going to find KE. So the key here is V2 is equal to 2 times V1, since we're going double the speed. So we look here and we do this M. V2 is really 2 times V1, so let's put that in there. Okay, and then we're going to simplify it a little bit more. We're going to square 2V1, because that's a quantity squared. So we would end up with M times 4V1 squared over 2, based on what we should be doing. Because order of operations doesn't really matter here, we can pull that 4 out, meaning we just make it look like this, and be 1 squared over 2. All I did there is just take that 4 and pull it out over here. So it's the exact same thing. Now, MV1 squared over 2. Oh, guess what? That's the exact same thing as KE1. So by doubling V, we actually quadrupled the kinetic energy. The whole reason there to go through this process, understand that this is not a linear relationship anymore. Kinetic energy is a squared relationship. You have that exponent right there. That 2 is going to mean that when we double V, we're actually going to quadruple the velocity. We triple V, we multiply the kinetic, we triple V, we multiply the kinetic energy by 9. If we cut the velocity in half, we'll cut the kinetic energy by 1/4. And that's all because of that squared exponential relationship there. So the second one's a little bit tricky. So we want to compare the speed of a brick drop from H with one drop from 2H. So we know that we know that VF equals the square root of 2GH from free fall equations. Or if we want to look at energy equations, we know here's our gravitational potential energy, here's our kinetic energy at the end, and V, M goes away, so V equals the square root of 2GH when we solve that. Okay, so let's say VF1 equals the square root of 2GH1. and VF2 is equal to the square root of 2GH2, but H2 is equal to 2 times H1. Okay, so let's put that in here. 2G times 2H1. Sorry. Now we could multiply these twos, but we're not going to. What we're going to do is kind of separate this into two things. We can make this the square root of 2GH1 times the square root of 2. And here's the reason why. Well, it's because what is 2 square root of 2GH1? Well, that's VF1. So this here is the multiplication factor. There's the ratio. So that's where that came from. Again, we're just comparing the same velocity, the velocity for one to the other based on the height change this time, as opposed to looking at just what happens to KE. So hopefully that makes sense. Here, the ball rolled up a ramp that's 90 centimeters high. How much work is done? Well, again, work equals FD. And the 250-gram ball means that it's going to require 250.250 kilograms times 10 meters per second squared to get the weight, times the height, which should be 0.90 meters. Again, distances need to be in meters. So if we multiply that all out, we do 2.3 joules worth of work to get it done. Now, what would its speed be at the bottom of the ramp if it fell? Well, again, that is converting all of that work we did into the kinetic energy of the ball. So you could do it this way, or you could set it up as our mgh1 equals mv2 squared over 2. You're going to get the exact same thing. Here we have 2.3 joules is equal to 0.250 times v2 squared over 2, and v would be 4.2 meters per second. Here, this would be 10 times 0.90 meters equals v2 squared over 2, and if we solve that, we would also end up with the same thing of 4.2 meters per second. Again, showing that work becomes the gravitational potential energy, which turns into kinetic as it falls. So here we have a block and tackle used by a local shipyard, had 5 supporting strands. It's found a lift that should be 10 to the third newtons, not times 103, and this should be 10 to the second, not times 102, but that's okay. Had 5 supporting strands. Each one of the supporting strands will support some of the weights, so that means each one of those is going to add to the IMA. So the IMA is 5. There's no math whatsoever. We don't know anything about distances other than how far it's lifted. All we know is that it had 5 supporting strands, and each one of those should help our system. The AMA, again, is equal to F out over F in. And the output for lifting this thing, remember, is the weight of the object. So that's 2 times 10 to the third, or that's a 2,000 Newton boat. And to lift that 2,000 Newton boat, it took 500 Newtons worth of force, meaning that even though we were hoping for a benefit of 5, we only really got a benefit of 4. What is the efficiency of this block and tackle? Well, there's efficiency, and efficiency, again, is just our score, AMA over IMA, and that is 4 over 5, or 80% efficient. One thing of note here, this 3 meters that we lifted the boat, even though we lost forces, the distances would still be the same. So the D in would still be 15 meters because we have to pull 5 times as far to lift it the same height. even though it's not perfectly efficient, we still have that to deal with. The distances would still be the same, even though the forces are different from the ideal situation. Last one, from a height of 2.15 meters above the floor, Larry Bird tosses a shot straight up toward the basketball hoop. With what initial vertical speed must the ball be thrown to just make it to the rim? The rim is 3.04 meters. The ball's mass is 0.600 kilograms. Again, here we're not really looking, we don't actually care about the size of the ball. Whatever size the object is doesn't really matter because we're talking about speed, not about force needed to push it up. So initially we have a height and we also are going to have a speed. So we're going to have gravitational and kinetic energy. When we get up to the top, this is where this question is a little tricky. We're going to try and get to stop right there. That's going to be the peak of its motion. So in that case, we only have a height. Remember, the peak, the velocity is 0. We're not moving upwards or downwards yet. Again, so we see we don't need the ball's mass at all. And we have 10 times 2.15 meters plus v1 squared over 2, which is our unknown. And then we have 10 times 3.04 meters. And from there, we just solve, isolate, multiply those two, subtract, multiply these two, subtract them from that side. And if we do that, we get everything to work out, sorry. V1 should be 4.2 meters per second. So hopefully these solutions helped. They're not, hopefully the problems aren't too hard. Again, I'll probably get you guys more information about the format of the test going forward, but hopefully this at least helps you in terms of getting prepped for some of the things, and I'll send out more information as to when we're going to do the test and kind of what that's going to look like. So anyway, I hope, do you have any other questions? Please let me know. Don't be afraid to reach out. Okay, bye.